everyone. Today in this session we are going to discuss about the Boolean algebra. First we'll see the introduction of the Boolean algebra. An algebra that deals with binary number system is called an Boolean algebra. It is very powerful in designing logic circuits used by the professor of computer system. The basic logic gates are called as the building blocks of all the circuits in a computer. Boolean algebra derives its name from mathematician George Boole in the year 1815 to 1864, who is considered the father of symbolic logic. Boolean algebra deals with truth table, true and false. It is also called as switching algebra. Binary valued quantities, variables and constants. A variable used in Boolean algebra or Boolean equation can have only one of the two variables. The two values are false or true. A sentence which can be determined to be true or false are called logical statements or truth functions, and the results true and false is called as the truth values. The variables which can store the truth values are called logical variables or binary valued variables. These can store one of the two values 1 or 0. The decision which results into either 0 or 1 is called binary decision. Next heading is truth table. A truth table is a mathematical table used in logic to computer fundamental values of logical expression. A truth table is a table whose columns are statements and whose rows are possible scenarios. Example, consider the logical expression, logical statements. Meals is equals to Ram prefer rice and roti for the meal. So how can we write this expression in the form of the truth table? Y is equals to A and B. The logical variables are y, comma A, comma B, and the logical operator that we are going to use are AND operation. If the result of any logical statement or expression is always true or 1, then it is called tautology. If the result is always false, then it is fallacy. Next heading is logical operators. There are three logical operators: not, or, and. These operators are now used in the computer construction known as switching circuits. First one, not operator. The not operator is a unary operator. This operator operates on single variable. The operation performed by not operator is called complementation. The symbol we use for it is bar. X bar means the complementation of the x. If x is equals to 1, x bar is equals to 0. If x is equals to 0, x bar is equals to 1. The truth table and the Venn diagram of the not operator is so same thing. If x is equals to 1, x bar is equals to 0. If x is equals to 0, x bar is equals to 1. Next one, OR operator. The OR operator is a binary operator. This operator operates on two variables. The operation performed by OR operator is called logical addition. The symbol we use for it is plus. Example, x plus y can be read as x or y. The truth table and the Venn diagram for the OR operator is when both the inputs are 0, it is 0. If any one of the input is 1, the output is 1. AND operator. The AND operator is a binary operator. This operator operates on two variables. The operator performed by AND operator is called logical multiplication. The symbol we use for it is dot. The symbol we use for the AND operation is dot. For example, x dot y can be read as x and y. The truth table and the Venn diagram of the AND operator is if any one of the input is 0, the output will be 0. Otherwise, it is 1. Next heading, evaluation of Boolean expression using truth table. To create a truth table, we should follow some steps given below. Step 1. Determine the number of variables for n variables, create the tables with 2 to the power n rows. For example, if there are two variables x and y, then the truth table will be of 4 rows. If there is three variables x, y, z, then the truth table will be 2 to the power 3, that is 8 rows. That is first step that we have to follow while creating the truth table. Second step, the list the variables and every combination of 1 and 0 for a given variables. All the combinations we should write as an input. Create a new column for each term of the statement or argument. If the two statements have the same truth value, then they are equivalent. Then the truth table are said to be equivalent. Consider one example. Consider the Boolean expression f is equals to x plus y bar. This expression has two variables x and y. So how many rows? 2 to the power 2 is equals to 4 rows. So list the variables and the every combinations of x and y. What are the combination of x and y? That is 0, 0, 0, 1, 1, 0, 1, 1 are the combination of x and y. Create a new column y bar of the statement and then fill the truth table of y in that column. Then the final column contains the x plus y bar. So what is y bar? 1 0 1 0. X plus y bar is, so we have to do the AND operation for the OR operation for the x and y bar columns. So that is 1 0 1 1. Next heading, Boolean postulates. The fundamental law of Boolean algebra is called as postulates of Boolean algebra. These postulates for Boolean algebra originate from three basic logic functions: AND, OR, and NOT. The properties of 0 and 1. If x is not equals to 0, then x is equals to 1. If x is not equals to 1, then x is equals to 0. OR relation, logical addition. 0 plus 0 is equals to 0, 1 plus 0 is equals to 1, 0 plus 1 is equals to 1, 1 plus 1 is equals to 1. This is the OR relation. If any one of the input is 1, then the output will be 1. AND relation. AND relation is nothing but logical multiplication. If any one of the input is 0, the output will be 0. That is 0 dot 0 is equals to 0, 1 dot 0 is equals to 0, 0 dot 1 is equals to 0, and 1 dot 1 is equals to 1. Next one, complement rules. 0 bar is equals to 1, 1 bar is equals to 0. Principle of, next heading, principle of duality theorem. This is very important principle used in the Boolean algebra. The principle of duality states that changing of OR sign to AND sign, changing of AND sign to the OR sign, replacing 0 by 1 and 1 by 0. That is called as the principle of duality theorem. The derived relation used, the duality principle is called dual of the original expression. For example, take postulates 2. Second postulate you take, then the related to the logical addition. Then 0 plus 0 is equals to 0, 0 plus 1 is equals to 1, 1 plus 0 is equals to 1, 1 plus 1 is equals to 1. This is the second postulate. Now, working this above relation according to the principal duality theorem. Plus is changed to dot, 0 is replaced by 1. So then how it will be? 1 dot 1 is equals to 1, 1 dot 0 is equals to 0, 0 dot 1 is equals to 0, 0 dot 0 is equals to 0, which is nothing but same as that of the postulate 3. So that is related to logical multiplication. So 1, 2, 3, 4 are duals of A, B, C, D. Find the duals of the following expression. So you can see the expression number 1, x plus 0 is equals to z. So how can we change that? Just we need to change the sign and the wherever 0 is there, we will make it as 1. Wherever 1 is there, we will make it as 0. So x plus 0 is equals to x will become x dot 1 is equals to x. X plus 1 is equals to 1 will become x dot 0 is equals to 0. X dot x bar is equals to 0 will become x plus x bar is equals to 1. X dot y plus z is equals to become x plus y dot z. X plus x dot y is equals to x plus y will become x dot x plus y is equals to x dot y. Like this the duals will be worked out. Next, Boolean theorems. Boolean theorem can be proved by substituting all possible values of the variable that are 0 and 1. This technique of proving theorem is called proof by perfect induction. So these are some of the Boolean postulates. First one is properties of 0 and 1. 0 plus x is equals to x. 1 plus x is equals to 1. 0 dot x is equals to 0. 1 dot x is equals to x. Next, independence law. X plus x is equals to x. X dot x is equals to x. Complementary law. X plus x bar is equals to 1. X dot x bar is equals to 0. Inversion law. X double bar is equals to x. Commutative law. X plus y is equals to y plus x. X dot y is equals to y plus x. X dot y is equals to y dot x. Association law. X dot y dot z is equals to x dot y dot z. X plus y dot z is equals to x plus of y dot z. Distributive law. X dot y plus z is equals to x dot y plus x dot z. X plus y dot z is equals to x plus y into x plus z. Absorption law. X plus xy is equals to x. X into x plus y is equals to x. X plus xy plus x bar y is equals to x. X plus y into x plus y bar is equals to x. X plus x bar y is equals to x plus y. X into x bar plus y is equals to xy. So these are all the Boolean postulates. Next one, De Morgan's theorem. It is a very important part of the Boolean algebra. Very important theorem, that is De Morgan's theorem. We have two De Morgan's theorem, De Morgan's first theorem and De Morgan's second theorem. First we'll see De Morgan's first theorem. The statement of De Morgan's first theorem is when the OR sum of two variable is inverted, this is same as inverting each variable individually and then adding these inverted variables. So that can be written as x plus y whole bar is equals to x bar dot y bar. We can prove the De Morgan's theorem. First theorem by using the truth table. How can we prove? So first we have to take what are the things that is required. X, Y, X bar, Y bar. LHS we have to take X plus Y whole bar, X bar dot Y bar. These are all the things that we require. The last two columns indicates that the LHS and the RHS. So first we should take X bar. X bar is the complement of X, that is 1100. Y bar is the complement of Y, that is 1010. X plus Y will be 0111. X plus Y whole bar will be 1000. X bar dot Y bar will be 1000. So as we compare the last two columns, both of the last two columns are identical. Hence, De Morgan's first theorem is proved. Next one, De Morgan's second theorem. So how can we state the De Morgan's second theorem? When the AND product of two variable is inverted, this is same as inverting each variable individually and then ORing these inverted variables. So this can be written as x plus x dot y whole bar is equals to x bar plus y bar. We can prove the De Morgan's second theorem by the truth table. So same thing we have to take, but we have to take here x dot y whole bar, x bar plus y bar. So you can see last two columns 1110. Compare last two columns which are LHS and the RHS of the theorem. So both are identical. Hence we can say that De Morgan's second theorem is proved. Next one, applications of De Morgan's theorem. It is used in simplification of the Boolean expression. De Morgan's law commonly applied to text searching using Boolean operators and, or, and not. It is useful in the implementation of the basic gates operations using the alternative gates. Simplifications of the Boolean expression. How can we simplify the Boolean expression? So why we need to do the simplification of the Boolean expression? Because simplification of the Boolean expression will reduce the simplification of the Boolean expression will reduces the expression. So the simplification of the Boolean expression is necessary. So how can we simplify the Boolean expression? There are two popular methods are there to simplify the Boolean expression. One is algebraic manipulation. Algebraic manipulation by using the postulates. And the second one is kernel map. So first we'll see the algebraic manipulation. How can we do the algebraic manipulation? I have given 4 examples. I'll take some 2 examples to explain. First I'll take the second example, xyz plus xyzw plus xz. This is the given expression. How can we simplify this expression by using the algebraic manipulation or by using the Boolean postulates? XYZ, we can take the XYZ common and the both in first two terms. So if we take the XYZ as the common factor, the remaining will be 1 plus W plus XZ. XYZ dot 1 plus XZ. Again we can take the XZ as the common factor. Remaining, remaining term will be Y plus 1. So the answer is XZ. Like this we can do the algebraic manipulation. Next term is min term. Min term is the product of all literals with or without bar within the logic system, or a single variable or the logical product of several variables. The variables may or may not be complemented. A variable may appear either in its normal form or in its complemented form. If the variable value is 0, then it is complemented, otherwise it is in the normal form. For example, if we have two variables x and y, there are four possible combination can be formed with the AND operation. That is x bar y bar, x bar y, x y bar, x y. These are the four combinations of the minterms. Those are designated as the small m, that is m0, m1, m2, m3. And each of these four AND operation represents one of the Boolean expression term and is called as the minterm or standard product. A symbol of each minterm is also shown in the table and is of the form mj, where j denotes the decimal equivalent of the binary number of minterm designated. For example, the minterm x y bar, whose combination is 1 x bar y bar z, whose combination is 1110, can be written as 6 as the decimal. So the decimal equivalent of 110 is 6. So a Boolean expression may be represented from the given truth table by forming a minterms for each combination of the variable, which produces has 1 in the function and then taking the OR logical addition of these terms. Assume the truth table x, y, z, the output will be given. They have given the output and the minterms also they have given. That is m0, m1, m2, m3, m4, m5, m6, m7. So that depends upon the truth table. The Boolean function of the truth table is obtained by ORing three minterms, that is 0, 1, 0, 0, 1, 1 and 1, 1, 0. Since each term of this minterm produces the result 1, so we have to take only those outputs. That is f of x comma y comma z is equals to x bar y z bar plus x bar y z plus x y z bar. So that indicates m2 plus m3 plus m6. The above Boolean function is sum of three product terms. This type of expression is known as sum of product expression. F of x comma y comma z is equals to the sum of 2 comma 3 comma 6, where f is a Boolean function with three variables x comma y comma z, and it can be read as function f is sum of second, third and sixth minterm. Sum of product. A sum of product expression is a product term or several product terms logically added. Find the minterm designation of the following. So x bar y z, the binary equivalent will be 100. What is the decimal equivalent? The decimal equivalent is equals to 1 into 2 to the power 2 plus 0 into 2 to the power 1 plus 0 into 2 to the power 0. So 4 plus 0 plus 0 is equals to 4. Like this we have other examples also. Next heading is max term. Max term is the sum of all literal with or without bar within the logic system, or a single variable or a logical sum of several variables. The variables may or may not be complemented. A variable may appear either in its normal form or in its complement form, x bar. If a variable value is 1, then it's complemented. Otherwise, it is in its normal form. For example, if you have two variables x and y, then there are four possible combinations can be formed with the OR operation. Each of these four operations represents one of the Boolean expression term and is called as the max term or a standard product. The symbol of each max term is shown in the table and is of the form mj, where j denotes the decimal equivalent of the binary number of the max term designated. So each max term is designated with a capital M. So for example, the max term x plus y plus z bar whose combination is 0, 0, 1 can be written as m1 as decimal equivalent, that is as decimal equivalent 0, 0, 1 is 1, so we have to designate with the 1. The Boolean expression may be represented from a given truth table by forming a max term for each combination of the variable, which produces has 0 in the function and then taking the AND of all these terms. As shown the truth table 0 0 0 0 0 1 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. These are the possible combination of the inputs. The output will be 0 0 1 1 0 0 1 0. And the max term that we have written has x plus y plus z, and the designations are m0 to m5, m7. The Boolean function of the truth table is obtained by ANDing 5 max terms, that is 0 0 0 0 0 1 1 0 0 1 0 1 1 1 1. That is x plus y plus z, x plus y plus z bar, x bar plus y z, y plus z, x bar plus y plus z bar, x bar plus y bar plus z bar. So that is equals to m0, m1, m4, m5, m7. The above Boolean expression is the product of three sum terms. This type of expression will be called as product of sum expression. So f of x comma y comma z is equals to, it is the sum of 0 comma 1 comma 4 comma 5 comma 7, where f is the Boolean function with three variables x y z, and it can be written read as function f, and it is the product of 0th term, 1th term, 4th term, 5th term and 7th max term. So the product of sum, a product of sum expression is a sum term or a several sum terms logically multiplied. Next heading is canonical form. Canonical form, Boolean expression expressed as sum of min terms and the product of max terms are called canonical forms. For example, the following expression are the min term, min canonical form and the max canonical form of the two variables x and y. That is, min term canonical will be like this: x plus x bar y bar plus x bar y plus x plus y bar plus xy. It is in the form of sum of product. Max term canonical form, it is in the form of product of sum, that is the x plus y bar, x bar plus y into x plus y. The minterm canonical expression is the sum of all minterms. Each minterm contains all the variables. The maxterm canonical expression is the product of all maxterms. Each maxterms contains all the variables. The conversion of SOP into canonical form. How can we convert? Convert the Boolean function f of x plus x comma y is equals to x plus x bar y into canonical form. So how can we do this? First we have to see the given expression and see how many variables are there. There are two variables x and y. So we have to see the missing variables. The first term x is missing one variable, that is y. So the missing variable should be multiplied with y plus y bar, because y plus y bar value is 1. Anything adding to the 1, the same value will be nothing, the logic is going to change. So x is equals to x into y plus y bar, that is equals to xy plus x bar y. So substitute that in the expression 1, in the equation 1, it will become xy plus x bar y plus xy bar. Here the term x bar y and appears twice. So according to theorem, if the expression appears twice, then we can write it as we can remove one. So xy plus x bar y. Rearrange the minterms in the ascending order. It will become x bar y plus xy. that is m2 plus m3. So the answer is 2 comma 3. Conversion of POS into canonical form. Convert the Boolean function f of x comma y comma z, that is equals to x plus y into y plus z. Here also we should see how many variables are there. Here we have three variables, that is x, y, z. Two terms also missing one variable, that is first term is missing z, second term is missing x. So first we will make it out first term into canonical form, that is equals to x plus y plus which is the missing term that we have to add with z plus z into z bar, because z into z bar is 0. 0 is adding to any expression will not going to change the logic. So by using the distributive law we can do that. And the second term here we are missing z, x into x bar we have to add. So final expression will be m0, m1, m4, 3. So this is about algebraic manipulation of simplifying the Boolean expression. Next thing is in the simplification of the Boolean expression is Karnaugh map, a graphical display of fundamental products in a truth table. The fundamental product, the logical product of variables and the complement of that produces a high output for a given input condition. A map method provides simple procedures for minimizing the Boolean function. The map method was first proposed by E.W. Rich in the 1952, known as Rich diagram. In 1953, Maurice Karnaugh proposed Karnaugh map. It is also called as K-map. How to construct a K-map? The K-map is a pictorial representation of a truth table made up of squares. Each square represents either a minterm or a maxterm. A K-map of n variable is made up of 2 to the power n squares. That means if it is a single variable K-map, a one variable K-map, the one variable K-map is written as f of a. There are two minterms, a and a bar for one variables. Why? Because if it has one variable, it has 2 to the power n squares. 2 to the power 1 is equals to 2 squares. In one variable K-map, one square represents one minterm. Two adjacent squares represents a function which is always true. F of a is equals to 1. Two variable K-map. The two variable Boolean expression are of form f of a comma b. There are four minterms a bar, b bar, a bar, b, a, b bar, a, b for two variables. Hence the map represents four squares. So 2 variables means 2 to the power 2 is equals to 4 squares. 3 variable K-map. The 3 variable K-map Boolean expressions are of the form f of a comma b comma c. There are 8 minterms because 3 variables 2 to the power 3 is equals to 8 squares. The order of variables is 0, 0, 0, 1, 1, 1 and 1, 0 in the gray reflected binary code. One should not use a straight binary code like 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. The straight one binary code will be used in the Rich diagram, but Mr. Karnaugh modified the Rich diagram and used the reflected binary code. 4 variable K-map. The four variable Boolean expression are of the form f of a comma b comma c comma d. There are 16 minterms of the four variable. Why? Because there are four variables. So 2 to the power n square means 2 to the power 4 is equals to 16 squares. The rows and columns are numbered in the reflected code system. So that is in the left hand side a bar, b bar, a bar, b, a b, a b bar. And in the right hand side c bar, d bar, c bar, d, c d, c d bar. According to that, so the four variables K map will be constructed. So there are these are the rules and the how to construct the K map and simplify the K map. This is about this session. Thank you.